Alright, so I solved the pawns and the refs, and we'll go through them. The first challenge was Echo, which was a basic pawn challenge. We can download the binary and we can look at it in Ghidra. Let's analyze it, why not? If we look at the functions, we can see there is a win symbol, which is just a function that prints the flag for us. So we can expect, based on this, that the challenge, that the solution for the challenge will be to override the return address. So instead of returning to some other function, we'll return to the win function. That's a standard kind of challenge. Yeah. Additionally, we can run pawn checksec on the binary, so we can see that the binary has no position independent code. This means that the program will be loaded in the same place in memory every time, so we know where the function is in the virtual memory space. Yeah, alright. Let's look at my solve script. The way I do it is by just sending the address 100 times. It doesn't really matter because in the main function we can see that there is a gets function which just reads an arbitrary number of bytes. It was just easier to send 100 times the return address than to manually check what's the offset. So we can see that it runs. I forgot the. Let's say in GDB. So there's our main function. You can see that there is the call to the gets function. It puts our input on the stack. So we can see that there are some values, and I will go to the next instruction. And now it's all overwritten with our win function. I can show you that it's the win function there. One thing that I do is I return not to the win symbol, but to win +5. I do it because when we look at the disassembly, there is a push RBP, and some functions in glibc expect the stack to be aligned to 16. So I don't know if in this case this will crash, but it often crashes, so I just do it out of habit to skip the push instruction. You can see that whatever. Yeah, so yeah, you can see that there is a 0 at the stack pointer, so it's nicely aligned to 16. And yeah, that's the challenge. You can continue, and this will scream at us that the flag takes the file is not there, but we executed the code that we mandated, and this would give us the flag if there was a flag. So yeah, that's it. Next challenge was let's go with this one first. Additional information needed. This is a very similar challenge to Echo, except there are some additional things. think it was is this one? Yeah, I think this one. Let me check. Yeah, this is okay. This one. If we run pawn check on the challenge, then we will see that nothing has changed. The code is still a position still isn't a position independent executable, so it will be in the same space in memory. One thing that changed is that now it's a 32-bit binary, except instead of a 64-bit binary. So if you know your calling conventions on x64, the arguments to functions are put in registers, but in x86 the arguments to functions are put on the stack. So yeah, if we look at the binary, it should be this one. Sure, analyze it, why not? Now it's the same kind of challenge where you have a main function with gets, but now if we look at the getFlag function, there are some conditions that it wants us to be satisfied. We cannot return to this place because there is some weird stuff happening with the EBX register. Looks like it's like used in the instructions there, but it's defined like all the way there. I don't know why this is happening, but it's like whatever. Basically, it just means that we have to return to the function properly from the beginning. Yeah, so there is an if statement that checks if two multiplied numbers are equal to some value, and since it's an x86 binary, the arguments are put on the stack, so we can just as we will say in the solve script, we can just put the arguments after the return value. The way I check the offset is by sending a bunch of random letters with the cyclic function. So after we run this in GTB, we'll see that it crashed at some random value, so I can just cyclic minus L. Shit. Alright. So we can see that the offset it crashed at is 40. And that's how I got the 40 value. It's a fast way to do it. We can do it by hand, but it's just easier to do it this way for me often. There is a times2 because there is some garbage value in between there. We can just write times1 and just put whatever there, like, I don't know. If maybe it's the ABP, I'm not really sure. Whatever, it's just some value that we don't care about, and we want to put the arguments on the stack after it. So we can run the program. Looks like the it's not the EP value. But it doesn't really matter. It's there we can see that our the values we pushed are taken from the stack as arguments. So if I hex dump this, you can see that at +8 is EBP plus 8. So at +8 there is 1 and there is 23, which is what we pushed in the solve script. Yeah, there's 23 and 1. So that's the solution. I return to this place and it doesn't crash, so maybe we don't need to skip the push at the beginning. It's whatever. It printed the flag. I created just a dummy file with the flag to check if it works, because I wasn't sure if it will crash. I think I don't remember doing honestly. Alright, so the next challenge was calculator, which was a pawn jail rather than a typical binary exploitation. Is it called binary exploitation? Yeah, I guess it's called binary exploitation, but there is it's not a binary. Yeah, it's a Python program. There is a blacklist which checks if any like the maybe from the beginning. I'm sorry. So we give the program some input. It closes the std in, but that doesn't really matter. And then it executes the input that we gave it, except it checks if any of the letters in our input are in the blacklist. So we don't want our input to contain any of the blacklisted letters. The way to go around this is because Python doesn't. There is one funny thing in Python. I have this in my notes. Yeah, that non-ASCII identifiers are translated to ASCII identifiers. It's like a very funny behavior. You can read there about it, why it even exists. What it means for us that like I can like code. If I write eval there, and I can just use the Python interpreter. Paste there the eval that I copied. It will be treated as a normal eval, as you can see. So the way I solved it is by encoding a string this way. I used from my notes a canned solution, so I didn't really have to think about it. You can read about it there. It's not my solution. I just stole it from someone. It doesn't work anymore, I guess. But unlucky. Anyway, this works by executing whatever is in there. So if I write ls, it will execute ls. The one thing that we didn't get rid of is the underscores. So to get rid of the underscores, we can just put it in another eval, and we can put it some string, and now there, instead of underscores, we can write the we can't write the hex code in the strings, so we have to encode the underscore in octal values. So to do this, yeah, we can, the octal value for the ASCII representation of underscore is 137. So we can just kind of write this like this, and this will be treated as two underscores. So I won't go over crafting the whole input. I hope this is enough of an explanation how to do it. Of course, instead of the ls there, you probably want some, like, I don't know, cat flag text or something like this. You get the gist. Alright, so the next challenge was Ultimate Algorithm Factory. Let's go over to Ghidra. If we run pawn checksec on the binary, you can see that now this time it has everything turned on, so it shouldn't be this easy to exploit. But this is not really an exploitation challenge in the sense that we don't want to get a shell, we just want to corrupt some memory to change the behavior of the program, I guess. Because if we look at let's go at the menu, and if we look there at the was access function, it checks if the money we have is more than 100, and in the expected behavior of the program we cannot go over 10, so we have to corrupt some memory to get there. And if we get there, print the flag. To do this, let's look at the Q upgrade algorithms function, which is like a very weird function. Depending on the value of how many upgrades we want, if for example we will give it the value of 5, then it will upgrade our algorithm we have chosen by 5, but after some time. There is a timer, as we can see there, and the timer goes down every iteration of the menu function or whatever. Now it's a -1, so if we write 3, then after 2 steps it will execute the upgrade. Yeah. One thing to notice to solve this challenge is that after well, maybe when we buy algorithm, then we can see there is a malloc 4. There's 4 bytes for the value of the algorithm, yeah, the money value is buy it for or sell it for. And in SNYK algorithm there is a 3. The 3 is not nulled, but it doesn't really matter what matters for us is that mm, the the Q upgrade variable still points at the point in memory it pointed to before. It like it doesn't know about the fact that that the algorithm is solved. Yeah, so we can abuse this fact to either corrupt heap metadata, which won't be useful for us. What we want to do instead is mm, to uh, what we want to do is to buy an algorithm, upgrade it for free, so 2 steps later it will do the apply function. Now we have 2 steps before it's upgraded, so we want to sell it. We want to buy an algorithm for 1, and because of how the malloc function works, it returns the same address from tcache, which is then overwrote in the apply upgrade function. And basically it overwrites a 1 to an 8. So we can see that it works. If the description wasn't clear enough, I'll just go. So we buy an algorithm for 5. We want to buy an upgrade for free. So we have now 2 steps, 2 turns, I guess. We sell it. We buy something for 1. And I fucked something up, or oh no, it's fine. Okay. And now the value is 14. So we can do this in a loop, and we will end up in whatever value we want. Yeah, like I end up there with 114. So now I can access the flag. And that's the POM challenges. Now let's go to the reverse challenges. I don't have this downloaded anymore, I think, so I'm gonna download it again. So the program wants a passport from us. Does the challenge says anything in the description? I guess not really. We can look at it in Ghidra. We can see that there is some function we don't really care about, and there is a string compare with our input. So this means that the flag or the password is not encrypted in any way. We can just look what's the value in the strcmp function. So I do it in a debugger. I just break on mail. There are no symbols, so I can just run. I can press Ctrl C to step out of the debugger. Now I want to break on strcmp and to continue till the function is executed, like whatever. And I want to see what are the arguments for the function. In x64 calling convention, the first argument is in the RDI register, and the second argument is in the RSI register. So you can see that the password is unlock me 123. It's correct. And that's the challenge. The next one was a powerful shell. Which was just like a weird PowerShell program. I don't know what it does. If you decode this string with just base 64, so I guess just decode it. There is some other x64 base 64 string. I can decode it again, and there's the flag. I don't know what the program does. Whatever. The next challenge was string me along. It says something about string, so we can maybe predict that we have to use the string function. And it asks us for a password again. Like I said, we can use the string function there. It like if we look at the strings, we can see that there is a flag, and there are some other weird stuff in the next lines. So it turns out that if we copy this and we remove the weird H letter, because this is not a hash like the rest of the, like we can see that the H letter looks weird, so we can just remove it, and this is a correct guess, and this is our flag. Anyway, alright, so its go time was a weird challenge, so I will leave it to the end. Let's go with letters to nums first. Do I have the challenge somewhere? Yeah, I have it. Alright. So if we run the binary, and it does maybe nothing we could think, but what it does, it reads the flag txt program, and then it encrypts it in a way we don't know, and it saves it in the end flag. Yeah. At the beginning I tried to black box it, but it didn't go well, so I just gave up on the idea, and instead I actually did the change properly. If we look at the Ghidorah compilation, we can see that the I guess the C. I don't fucking remember. You mean the right flag? Yeah, it's the alright, it's the uncode cars, which puts two. I'm sorry, which puts two characters together, and then it prints it as a number, so we can reverse the operation. Like we take this number, for example, go to Python, we can check the hex value, and the half of the the hex value is one letter, and the second half of the hex value is another letter. So we can check this that it's true. And if we do this for the whole thing, then we will get the flag. Oh, this is a challenge. This is just some basic bits operations. Like we shift the whole thing so it doesn't overlap, and then we use the bitwise OR operator to connect the two characters together. So I thought that was the challenge. Now let's go to the next one, which is math for me. I don't remember what this was about, honestly. Alright, let's look at the binary. Sure, why not? It checks some number. Alright, it checks some number and then it uses it while computing the flag, so we cannot just use the compute flag function. We have to actually give it the correct number. The way I did it was by brute forcing it, I believe. Yeah. If I run this, then it gives me 20, and 20 is the answer. This is a weird flag. It looks broken. It's correct. They even say it in the description. Alright, let's go with the next challenge. I don't remember this either. So let's look at the Gizrada compilation. Looks like it decodes the flag, but it doesn't depend on any value, so we can just print the execute the decode flag function. That's my guess. So that's what I'm gonna do. How's it called again? I don't think I don't have I don't think I have this challenge. Oh, alright. For run this in GDB, I can break at this strcmp. So I will just run the program, Control C. Now I want to break on strcmp. Continue. Is there any length check? There isn't any length checks. Okay, so I can just throw whatever there. I have my whatever value with whatever compared. I don't really care about that. I just finished the execution of the strcmp string, and I will override the rax register to 1, so the check goes like if it was the same thing, and print some stuff. Is it printing? Oh no, it's only decoding. Alright. And now it prints for us the flag. I hope the solution is correct. Honestly, I don't remember. It looks correct. Yeah. The next challenge was crabshell. The way I solved it was very cheesy, but a solution is a solution nonetheless. I don't believe I used the script for anything. Yeah, I just used it for sending the bytes because it has some really bytes. If I run the program in GDB, oh, this is a Rust challenge, by the way, which is not something we want to look at honestly. When you see a Rust challenge, you just want to run. So there are a bunch of like weird symbols, and you like don't know what's happening there. So I guess the challenge is to understand what's happening. If I run the program, it wants 16 bytes from us. So like 4, 8. Let me go with C. 16. Well, I guess I should just finger again. And now we are in main. We can see that there is somewhere in memory there is our string. I don't really want to think about it now, so I'm just gonna step through the function. It calls trim on our string, so it probably just removes the new line from it. We don't really care about that. I just step through it like we don't really care. Something happens there. I think I fight it up. Yeah, so what I'm gonna do is I'm gonna run the challenge again. I'm gonna find in memory our string. Maybe first I want to finish the function, and let's find till the trim is called. I have those two places in memory. I want to put a watch point there, so if the value is red, breakpoint will trigger. And we'll just continue, and we see that the value is compared to 31. It compares only the first byte of our thing, which would be should be I. Yeah, it will be I. So hex down. It's I. And it compares it to hex 31, which should be 1 in hex. So if we look at our solution, there is 1 in the string I sent. I'm gonna continue once again. It doesn't. Alright, so I'm gonna do this thing again. At least we can see together how the the process works. Ah shit. I wanna get out of this. think there are some breakpoints that are hitting. Alright. Oh shit. Alright. So there we have the comparison. I will just so I want to continue the execution. So to do this, I will have to override some flags, I guess, or just look at the disassembly. So let's guess I can just. The next instruction is at plus 171, so I can just set RIP to this. Up in the contact, we can see that we are there. And now some weird hex value is moved to the register RCX, and it's compared with our RIX plus 1, so it's RIX and plus 1, so we compare it with those 8 bytes. And because the values in x64 architecture are encoded little endian, we go from right to left and not from left to right. So the first character would be 26, then it would be 1F, then it would be the next one, and so on and so on. And we can see that there is some character, and then there is 1F, and then we can see that there's some character and there's 1F, so we can confirm that, yeah, this is the solution. I'm just gonna do the same thing again. I don't want to check now how to change the flag, and I don't really remember. It would be better to just change the flag on the register, but it is what it is. And then we can see that there are some other values. So we do this again. I can disassemble this. And there is the last value. No, it's not the last, but this one is correct, so I don't have to change it. And there are some two other values, two other characters, I guess, let's say. We can see that this is what we have in the solution, and there is one more, so I can disassemble it again. And there is the next comparison to 68. So yeah, if we send this the program, it will give us the flag. Now with it's go time, it was, I don't know if it's a broken challenge. It wasn't really working for me the normal way. Close it. It's go time. If we look at the main function, Where is the main function? I guess this is the one. I don't know really what's happening there, but we can guess by just stepping in GTB, looking at different things. We can see that eventually it will go to validate byte, I believe. Yeah, it will go to this function. I just found it randomly by playing with the program in GDB, and the name looks like it's what we are searching for. So the compilation is not possible to understand. I mean, it's kind of possible, but it's not really something that I like. We can see that there are some expected bytes, so we can guess that this is our flag or our key or whatever, and we can make some assumptions that this is the value is there. There is a not operator on the value from expected bytes, and there's some other value which has our input character. Maybe we add the index to it, and then we XOR with 42. This is what I've tried to do based on the bytes from there, but honestly it wasn't working for me, and I don't know why. So out of frustration, I solved it in an easier way. I don't say it. Another thing is that Go programs are very hard to debug because there are like multiple threads running for no reason. It's horrible. But if we put a breakpoint there, which is there is a comparison between the two values we loaded above. So I want to put a breakpoint there at the CMP instruction. I believe it is in history somewhere. Yeah. Let's go with the same string. Yeah, so the way I solved it is just by ignoring the comparison. So it takes the value from RCX and RDX and it checks if it's the same. But if we overwrite, let's say, the value, we can overwrite the both values. I'm not sure if we can overwrite the both values, only one though. I think it shouldn't matter. So if we overwrite the RCX register to the value of RDX register, then the comparison is correct, and we can do this multiple times. You can just do it in a better way, but I don't remember how to execute some code on every breakpoint. I just kind of forgot, so I'm just gonna do it like this. And it gave us the flag. Yeah, it's a very ugly selection, but it is what it is. So yeah, this is the challenges. I hope you learned something. Have a nice day.